So to finish up our fluids unit, we're going to talk about Bernoulli's principle. Another weird word. There's a lot of weird words in this. Bernoulli's and buoyancy. But stuff's pretty interesting. Like, this is why airplanes fly. This is why your shower curtain tries to attack you while you're taking a shower. And we'll explain why that happens. See, there he goes flying around. Crazy Bernoulli. So what does Bernoulli's principle actually say? It says, in a fluid flow situation, such as water or air, the pressure in the moving fluid is lower at places where the speed of the flow is greater than at places where the water flow is slower. Blech. In other words, when the speed of a fluid increases, the internal pressure in the fluid decreases. So speed increase, pressure decrease. So speed is inversely proportional to pressure. Inversely proportional. So why does the pressure decrease with velocity? So we know the pressure equals the force exerted per area, or P equals F over A. So while the fluid as a whole moves with any certain velocity, the atoms that make up that fluid also move around or jostle. This jostling in the atoms creates pressure. So if you have water in a glass, there's all these little atoms, and they're flying and hitting the side of this container. And this causes the pressure, because it's an outward force. So think of water in a container. While the water is not moving, the atoms that make up the water are jostling around within the container, and as the atoms move and collide with the sides of the container, they exert a force on the container, which creates pressure. Now, so if these atoms start moving, like if this was a trough, and I started emptying this trough, instead of hitting the sides of the container, they're just going to flow straight out. It's going to decrease the pressure because there's less of them smacking the sides of the container. And that's why when the velocity increases, the pressure decreases. So here it is again. Pressure in a moving stream exerts less pressure than the air surrounding the moving stream. So not only does it work with water, it also works with air. So let's say we have a barrier here, and on one side we have a quick stream of air flowing across it. This creates an area of low pressure. Now on the other side we have a slow stream, so it has a high pressure. So this goes really fast, and this is slow, like so slow, maybe even still. It's going to create this force, high pressure over here, low pressure over here. It's eventually going to make this barrier go that way. I'll give you some examples of that here shortly. And here's one of them. So a chimney, so when air moves across the top of a chimney, it has a higher velocity than the air at the bottom of the chimney in the fireplace. This means that there is a low pressure above the chimney, lower pressure than there is in the fireplace. So the smoke is drawn out of the chimney to the area of the low pressure. So if we didn't have Bernoulli's principle, if you have a fireplace in your house, you'd all die of carbon monoxide poisoning. Where's my house? Here's my house. Alright, so you got a fire down here in your fireplace. Fire. Alright. Then we got some air outside. It's flowing across the top of your fireplace. So there's a low pressure out here because we have a higher velocity of air. So low pressure because I spelled pressure wrong. Pressure because higher velocity. Inside your house, hopefully you don't have, a very drafty house. So there's not a lot of velocity of air moving around there. So it's a high pressure inside the house. So we got high pressure here. So this difference in pressure, this high pressure and the low pressure, is going to push the smoke up your chimney and out of it. So that's how chimneys work. You can try this one at home. Very simple. It's probably safe to do. You don't think you need goggles or anything. You might get a paper cut on your eyeball. But if you take a piece of paper, hold it out in front of you, and it's all limp, and blow across the top, what do you think is going to happen now that you know a little bit about Bernoulli's? Well, the paper is going to rise. So it's limp right now. I blow across it. It's going to rise like that. That's because there's a high pressure down here, low pressure above it. It's going to rise. So why? Because the breath speeds air molecules, which increase the pressure on top of the paper, and the pressure underneath the paper pushes it up. Kind of cut off my umbrella word there. It's weird. Should say inverted umbrella. So if you're ever walking out in the rain and your umbrella folds inside out, it's because of Bernoulli's principle. So the wind blows across the top of the umbrella, and so the air molecules that speed up on top of the umbrella, man, I have all kinds of typos in this, type of umbrella, therefore the pressure decreases outside of it. So here's your umbrella, you got air flowing over it pretty fast, but you got your head underneath here, not a lot of wind. So we got high pressure here, low pressure here, umbrella pops out. Like I said, air in the umbrella, greater pressure because there's less velocity of air. And the shower curtain. Why the shower curtain stinks sometimes in the shower, especially if it's cold in your house, like it is in mine. So Bernoulli's principle explains what happens to your shower curtain too. So it's hot inside the shower. So air molecules speed up inside the shower. Therefore the pressure decreases inside the shower. And air outside the shower with more pressure pushes the shower curtain in. So now you're taking your bath, splish splash, I was taking a bath. And here's your shower curtain. And over here we got cold air, not moving. Velocity equals 0. And over here, hopefully you take warm showers. If you take cold showers, this wouldn't happen. Hot. So it's going to make all these molecules of air, because we know when we speed stuff up, the molecules are going to increase their kinetic energy. So they're going to speed up. So their velocity is going to increase. Velocity goes up. So because we have a higher velocity over here, we have a lower pressure. Low pressure, high pressure. And it's going to make your shower curtain go in, because this high pressure is going to push it inwards and attack you. It's also how we can change our voice, why we sing. So when you speak or sing, a stream of air is moving through your vocal folds from your lungs. So since the air has a high velocity, an area of low pressure is created between your vocal folds. So here's your vocal folds right here. We breathe outwards, so we got air coming out here. So we have a velocity of air coming towards us. And it's going to cause your vocal folds to like come into each other. These guys are going to go in a little bit. And we can control how much air is coming out of our lungs, so we can control how far closed our vocal folds go. And this is how we sing or speak. So the vocal folds are pulled inwards because of this drop in pressure. So now the pressure from the outside of the vocal tract is greater than the pressure between the folds and pushes the folds together and creates speech. So immediately the folds are forced opening in by the airstream that is still coming from your lungs, and this causes the Bernoulli effect, and this cycle continues forever and ever, and this is why we sing. So we can also apply this to instruments if you play an instrument. So reed instruments, the Bernoulli principle acts on the reed and the mouthpiece. The velocity of the air from the musician's breath creates a low pressure between the reed and the mouthpiece, which causes the reed to vibrate. So you have, here's your reed, we're blowing air across it. So we're blowing air in right here. And it's going to cause this thing to go down, and it's going to spring back up. So it's going to vibrate. It's going to wiggle back and forth. And it creates vibration and makes our reed instruments work. And it's also why brass instruments work, because Bernoulli principle acts on the musician's lips, causing them to vibrate similarly to the vocal folds. So if you ever, can go with your lips, that's because of the Bernoulli principle. And I tried to get a video of my son doing that, but he just was not cooperating. He's very camera shy. A little kid will be funny as hell until you put a camera on him. All right, and another example. So here, where's the picture? Oh, I should have the picture come up first. So we take two ping pong balls, suspend them from strings, and we blow air in between them using a straw or something. We have normal pressure on the outsides of the balls, but in between there's an area of low pressure. So the balls are going to move towards each other. because we're increasing the velocity, therefore decreasing the pressure in between the two ping pong balls. That's also why airplanes fly. So it allows not only airplanes but birds to fly as well. So actually, the secret behind the flight is underneath the wings. And I'll show you why. So here's your typical wing. I don't really like the way they drew this. Didn't really show it too well. Here, I'm going to draw a little bit more on here in purple. So this is like what the wing actually looks like. It's flatter on the bottom than it is on top. It's more humped on top, like this. So as the air comes towards the wing, some of it's pushed over, some of it just goes underneath. Now the air up on top of the wing has a greater distance to travel than the air on the bottom of the wing, but it's still going to reach the air, or they're going to reach the back of it at the same time. So time is equal. So particle of air here, particle of air here. This one has to travel faster because it has a greater distance to cover in the same amount of time. So since it's going faster, we have low pressure up here, high pressure down here. Therefore, we create an upward force, which we call lift, and that's how wings work. The wings of your airplane. So in words, the air on top of the wing must travel a longer distance than the air below the wing, but air on both sides must reach the end of the wing at the same time, and therefore the air on top of the wing is traveling faster, equals less pressure, causes the lift. Air hits it. We got slow air on bottom, fast air on top. Creates lift because the pressure differences on each side of the wing. Here's actually a schematic that NASA has come up with. It shows the amount of pressure, and you can see everything in blue is pretty low pressure, and everything in red is pretty high pressure. So red and yellow, pretty high. So we have higher pressure underneath, lower pressure on bottom, and that's how airplanes fly, because it pushes it up. Now why they have those flap things is because it'll more even out the pressure, and that'll allow us to descend. So in this picture, the plane's actually ascending. But if you say like raise the flaps, like they'll raise the flaps like this, and it'll create a higher pressure above than below, and it'll push the airplane down. So here's just another schematic showing the different pressures. Again, blue, low pressure, red, high pressure on bottom, low pressure on top. Airplane's going to fly. So Bernoulli is why we are safe when we fly in those ginormous airplanes. Hope you enjoyed your unit on fluids.